This is a joint work by collaborators from the UK, the US, and Singapore. So we are also talk about the Stackelberg Games, which have been shown in the previous talk, I think. So Stackelberg Games have attracted much attention in the AI community in the recent years. At a high level, a Stackelberg game is played between the leader and the follower, where the leader commits to a strategy first, and the follower plays next after knowing the leader's commitment. So the Stackelberg equilibrium captures the situation in which the leader commits to her optimal strategy, and in consideration that the follower is always going to best respond to whatever the leader commits to. It is well known that a Stackelberg equilibrium can be computed very efficiently, and there are many applications of Stackelberg games, such as security games, which we have seen from the previous talk, and also exam design, contract design, and in some sense, even mechanism design problems can be viewed as Stackelberg games at a high level. Same as many other applications of game theory, these applications of Stackelberg games rely crucially on information about the player's payoffs. So as from the leader's perspective, if she wants to compute her optimal commitment, she needs to know about the follower's payoffs. In reality, however, a leader usually faces a follower with an uncertain type, so whose payoff parameters she is not sure about. And there are many approaches to address uncertainties, and one approach here is to let the leader to learn her optimal commitment by interacting with the follower and observe the follower's best responses to certain carefully chosen leader strategies. So to see how this can work, let's take a look at a toy example here. So here we have a 2x2 game. The leader is a row player, and the follower is the column player. The follower can be one of the two types, type A or B, which the leader is not sure about. So to figure out the exact type of the follower, the leader can simply play a mixed strategy 0.6, 0.4 here, by which I mean playing her first row action with probability 0.6 and her second row action with probability 0.4. And in this way, the leader is able to tell these two follower types apart, because these two follower types are going to respond to this leader mixed strategy in different ways. So for the type A follower, his best response to the leader strategy is to play action 1, and for this type B follower, his best response is to play action 2. So the leader can then obtain her optimal commitment by computing the corresponding Stackelberg equilibrium. So there are a number of papers along this research line adopting similar ideas to design algorithms for the leader to learn either the follower's type or her optimal commitment directly. So, however, since this is a strategic scenario, it would be natural to expect that the follower may behave untruthfully in order to just manipulate the leader's learning algorithm. So the problem here is if the follower can really be untruthful, the previous learning approach might be problematic. And to see what can go wrong, let's go back to our example here. So in this example, the leader's optimal commitment against each follower type is the following. When the follower is truthful, the leader is going to learn the follower's true type and then play the corresponding optimal commitment. And in this example, both follower types are going to respond by playing action 1. And this gives the following player utility in this game. So here we make the assumption that the follower always breaks ties in favor of the leader when he has multiple best responses. So as we have also seen from the previous talk, so this is a standard assumption in the literature, and it can and it is without loss of generality, because the favorable follower action can always be induced if the leader deviates from her optimal commitment by an infinite small amount. So for example, here, if the leader plays her second row action with slightly higher probability, the follower is going to strictly prefer taking action 1 in this example. So let's see what can happen if the follower is not truthful. So observe that here for a type A follower, actually the leader's commitment on type B is better for him because that would give him a higher utility. So in this case, it would be tempting for a type A follower to think, hey, if I can somehow get the leader to play his commitment on type B, then that would be better for me. And in this case, it's actually very easy for a type A follower to get the leader to play his optimal commitment on type B. So a type A follower here can simply pretend to be a type B follower and respond to the leader's learning algorithm according to the payoffs of a type B follower. Since the leader is learning the follower's type by observing their responses, in this case, the leader is going to learn that is going to be misled into believing that the follower has true type B and play her optimal commitment on type B accordingly. As a result, the type A follower's utility increases from 0 to 1, but the leader's utility drops from 1/2 to 0 in this example. So in this paper, we call this kind of deceptive follower behavior imitative follower deception, where a follower behaves constantly according to the payoffs of a different follower type. So this is perhaps one of the simplest form of deception, and it can be implemented very easily in practice. And in this paper, we aim at answering the question of how to play against such imitative follower deception. So here is our idea. So recall that when the follower is truthful, the optimal thing for the leader to do is to simply always commit to the optimal strategy against the type the follower appears to be like. But in the case that the follower might be untruthful, this might not work well because it may incentivize a follower to lie about their type. So the idea here is let's change the leader's commitment by playing something different than what appears to be optimal. So specifically, we now let the leader's commitment be given by a menu, which we call a leader policy here. And the menu specifies the leader's commitment against each follower type. And then the follower can pick from this menu whatever strategy they want the leader to commit to and imitate the corresponding follower type to get the leader to really play that strategy. And let's go back to our example again to see how a leader policy can help improve the leader's situation in this game. So we have known that if the leader always commits to her optimal strategy, then what happens here is that a type A follower would be incentivized to imitate a type B follower. So it turns out that the correct thing here for the leader to do in this game is to induce a type B follower in a different direction, to induce the type B follower to play instead action 2. So this small change will, of course, bring a very tiny sacrifice in the leader's utility, which is 0.005. But the good thing is that this new policy is able to erase a type A follower's incentive to imitate a type B follower. Because in this case, suppose if the type A follower still imitates type B, then he has to respond by playing his second action as well. And as a result, his utility drops to minus 0.33, which is even lower than what he could have obtained if he behaves truthfully. And in fact, it can be verified that this new policy under this new policy, actually no follower type has any incentive to imitate a different follower type. And let's say if both follower types appear with probability 0.5, this new policy is actually able to improve the leader's utility by around 1/4, as compared to the case when follower deception is ignored. So now the timeline of our game is the following. So at the beginning of this game, the leader is going to announce his policy, which specifies his commitment against each follower type. And then the follower comes and observes the leader's policy and then chooses from this leader's policy a best type to imitate. And next, the leader is going to learn the type the follower imitates and then commit to the corresponding policy as specified by his policy. Next, the follower best responds to the leader's commitment and still as if he is the type he imitates. So eventually, the leader's commitment and the follower's best response combined will determine the player's utilities in this game. And specifically, we consider a Bayesian setting here. So the follower's type follows a distribution pi, which is also known to the leader. And now, at a high level, this whole framework can also be viewed as a Stackelberg game on top of a Stackelberg game, in which the leader commits to a leader policy and the follower responds to the leader's policy by imitate a best type. So our goal is to find the optimal leader policy that maximize the leader's expected utility over the follower types. So next, I'm going to introduce our algorithmic results. So we provide an essentially complete view of the complexity landscape of the problem of computing the optimal leader policy. So first of all, the problem is unfortunately hard and hard even just to approximate. And the result holds even when we fix the number of follower actions to only 3. So this result can be shown from a reduction from the maximum independent set problem. So given a graph, a maximum independent set problem asks for the size of the biggest independent set on this graph. And an independent set is a set of nodes in which no 2 nodes in this set are connected by any edge on this graph. So given such a graph, we then create an instance of our game. We create a follower type for each node, and we also add a special follower type, which is the orange one here. So the payoff parameters of the followers are set in a way such that each of these node followers, they have a tendency to imitate both their neighboring node types and also this special follower type. If they eventually choose to imitate the special follower type, then the leader is able to obtain a utility 1. But if they choose to imitate their neighboring follower type, then the leader can only obtain a utility of 0. So this gives the result that the leader's utility in this game is proportional to the number of node followers who choose to imitate the special follower type. And also, we set the payoff parameters in a way such that there is no way we can incentivize 2 neighboring follower types to imitate the special follower type at the same time. And this establishes the following correspondence between the size of the maximum independent set to the maximum leader utility achievable by any kind of leader utility. And then the inapproximability of this maximum independent set problem would then imply the inapproximability of our problem. So this is the idea. And then we also considered an incentive compatibility variant of our model. So incentive compatibility here requires that no follower type would have any incentive to imitate a different follower type. So unfortunately, this problem, this IC variant of our problem is still hard to approximate. And we also consider a generalization of our leader policy by allowing the leader to further randomize over multiple mixed strategies in her commitment, and we call such a policy a mixed leader policy. And so normally randomization over mixed strategy wouldn't bring any extra benefit for a player to improve their utility, but it turns out that it is the case in our model, and we have an example in our paper showing that using such kind of mixed leader policy, we can indeed further improve the leader's utility. But then we move into the computation of the optimal mixed leader policy. Unfortunately, the problem is still hard to approximate. But the interesting thing is that it suddenly becomes tractable if we further impose IC constraints here. And we also did some experiments to evaluate our approach. And so the idea is that our policy-based approach can indeed improve the leader's utility. And sometimes the utility can be even higher than the truthful case when the follower behaves truthfully throughout the game. And in conclusion, in this paper, we make the following contributions. So first, we identify this imitative follower deception issue in Stackelberg Games. And then we propose a policy-based framework to address this issue. And then we look at the algorithmic aspects of the problem of computing the optimal leader policy and provide an essentially complete view of the complexity landscape. And we also did some experiments to evaluate our approach. And in the end, some future directions. So first of all, we only consider the Bayesian setting in our paper. And of course, it would also be interesting to consider the non-Bayesian setting. And the other question is what if the follower does not have to imitate a different type throughout the game? Like what if the follower can switch, can switch to play something different after he has convinced the leader to learn the fake type? And also, what if the leader does not have any power to make a commitment to a policy? And what can we do to play against the imitative follower deception in this case? And in the end, we are also interested to study some more specific models, such as security game and pricing game. So a more specific game structure would hopefully help us obtain more results than in this general model. So I guess that's it. Thank you. Yeah, that's a good question. So in our model, we assume that the follower can only imitate a type that is in a known set. So we don't allow them to behave arbitrarily, because in that case, maybe it would look too fake, and then the leader would immediately spot that the follower is doing something very fake. So yeah, that's our setting. No, the second bullet says that so after the follower has convinced the leader into believing that he's some sort of a fake type, then in the subsequent Stackelberg game, the follower here may respond according to, maybe switch back to their own true payoff and respond optimally. But in our model, they have to keep imitating this fake type and also responding according to the fake parameters.